start by giving the p at 1, right? So the first order as well as the 0th order. But it actually works out if you start with this arbitrary value, because it's not going to matter when n is equal to 1. The n minus 1 is equal to 0. Yeah, n minus 1 is equal to 0, so this, whatever you put here doesn't matter. Okay, and then if you didn't have access to polynomials, the derivative would still be unknown, right? So you have this other formula, which is it's minus n times x times p n, which is the Legendre polynomial degree n, plus n times pn minus 1 over 1 minus x squared. So it's complicated, kind of, and you have to derive it's complicated, kind of, and you have to divide by something with x's in it. So that formula is actually okay if you're going to evaluate as you go, because you don't need to keep track of the coefficients, so it doesn't matter that you're dividing by 1 minus x squared. Another alternative is to implement polynomial division, but we're not going to do that. Instead, we're just going to compute the Legendre polynomial, and then we're going to derive it symbolically, because we can do that. And then, so we have the two things we need. We compute the root using our guess. Using that information, we can compute the root using our root finding algorithm. And the weight is computed by this formula. And then you walk through all the roots. Okay, walk through all the roots, but where you start and where you end. We know that there are n roots because n is the number of points at which you're going to evaluate the function. So it makes sense. And it's actually going from 1 to n here, but we'll check if it works. Okay, so you compute the xi's, which are the roots. You compute the wi's. Then you sum wi times f at xi, which is fi in our notation. And that gives you the integral. But the Legendre polynomials work for integrals between -1 and +1. If you want something else, you're going to have to stretch the interval. So it's again, this is not going. It's not meant as this particular video is not meant as a careful walkthrough of how implementing the Gaussian quadrature. It's more a window through the thinking that goes on. So it's a bit more focused on just whatever thoughts pop up, and maybe unusually messy because I have to. It's a big thing, and I only partly remember it, which is, in my opinion, worse than not remembering it at all, because you don't know which memories to trust and which to distrust. Okay, so let's start with Legendre polynomials. In order to compute the Legendre polynomials, I'll have to go through the list of Legendre polynomials. If you really wanted to be very careful about memory, we could just keep track of the previous two Legendre polynomials, because the ones before that don't matter. And if an alternative to that is to just at the beginning of the program just compute until you reach the right degree, and then you have this table of Legendre polynomials that can exist for the whole duration of the program. Another way of doing it is to instead of using the standard allocator and then having 1 degree of Legendre polynomial living over there in memory, the other one living over there, you can reserve a bigger space of memory that everything can fit in, and then you just allocate as you go, but one after the other. You reach the final one that you want, and then you can copy that somewhere else and free all of this memory, so remove the memory constraints imposed by that. But we're not talking about big amounts of memory, and it's actually quite easy, I think, to make it so that you're basically consuming no memory, like just negligible amounts of memory. Something worth remembering too is, because of the arithmetic error, you can't go crazy too much. You can only go crazy a little bit, because after a while the precision gets worse. First of all, you hit the best precision pretty quickly, n doesn't have to be really big at all, and then it doesn't matter for a long time, okay? And then eventually the error goes up because you're doing too much arithmetic. So because the degree is small, the memory requirements are not that big, okay? And it's pretty easy to deal with, so let's just do the simplest thing of not caring at all, just having all of this separate, mess in memory, but not thinking about it. So I think starting to be pretty tired. Kind of used to the different time zone, but still I can't go to sleep too late because I always wake up like super early. So what we will do is make the Legendre polynomials. When you have kind of recursive things with an index, but you need to name it with a variable, it's okay, I find, to just use like the first two indices, because it makes it concrete, and you can't use negative numbers very effectively in names, but you can use positive numbers. Return notice that we also need to give the integer. Did I define integers in this file? No. Let's not use integers then. Unsigned integers, sorry. Alright, so P2, okay, P2 dot n equals to n, then so that's how we do it. Alloc poly, like this. You actually give it a degree. Okay. So this puts the